Today on StarTalk Special Edition, we learn about a hopeful new direction of cancer treatments and how they work. Could we one day rid humanity of this terrible, multifaceted disease that masquerades as our own cells as we try to rid them from our universe? Up next on StarTalk. This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist, serving as your host. Today, it's special edition. And I got with me my special edition co-host, Gary O'Reilly. Gary.
Hi, Neil.
Yeah, former soccer pro and sports commentator. I also got Chuck Nice. Chuck, always good to have you, man.
Hey, Neil.
So today, we're taking up the very serious topic, the emperor of all maladies, cancer. Oh my gosh. Gary, what did you put together for today?
Well, finding a successful treatment for cancer has long been one of medical science's biggest challenges, if not the biggest challenge. So, with variable results and some rather nasty side effects. But there was one particular cancer researcher at City of Hope Cancer Research and Treatment Center in Los Angeles decided, as she says, follow the science. And now we are looking at the possibility of a treatment that takes out the cancerous tumor, but leaves the healthy cells around it intact. I mean, this is the kind of science that really could change people's lives. And by the way, our guest once dreamed of being an astronaut. So, if you would like to introduce our guest, I think we're going to have an interesting show.
Okay, I'll introduce anyone who ever dreamed of becoming an astronaut. Linda Malkus, PhD. Linda, welcome to StarTalk.
Thank you so much. I'm such an honor to be here.
You're associate chair and professor in the Department of Molecular and Cellular Biology at the City of Hope Cancer Research and Treatment Center. So I'm just glad places like that exist in this world. And you have clinical expertise in molecular diagnostics and experimental therapeutics. So it sounds like you're all up in this. And so just welcome. And so tell us about cancer. Like what, I have basic understanding of cancer. What, Chuck? What do you
I was going to say, that sounds like the worst bedtime story request ever.
Tell me about cancer. So cancer is hard to treat, as I understand it, because the cells look just like your cells. So anything that would kill a cancer cell is going to kill your cell. And that's the beginning and end of what I know about cancer, basically. So what can you add to that? And what can you tell us about the new treatment?
Well, actually, you got a really good start with this in that cancer, I guess, in my opinion, is really kind of a way the body turning on itself. And cancer is like, being that you already know, I'm like a science fiction geek. So if you think of the movie Aliens, you can think of cancer as, the most perfect predator. It really is. And it's why it's so hard to treat, because it looks like us. It's our own body. It knows all our own tricks, it's our processes, which it uses against us. And then cancer also has this ability to constantly evolve. It's actually a very scary predator. It really is. And that's why it's so very, very hard to treat, because it's constantly changing itself. It is such a weird entity. That's how when I was first studying, I would really look at it as like it's a cell, but it's almost like a living entity. It is, if you think about it every day. And I want to congratulate you all. You're all cancer survivors. Every one of us, including myself. Every day since before we were born, we make at least 8 cancer cells, and our immune systems take them out. So we're constantly making them.
Wait, 8 cells per
day.
Every day.
Okay.
Per day.
Okay.
Per day.
Okay.
Per day.
Okay. So we're making at least 8 cancer cells every day. And your immune system is constantly surveilling and taking them out. We also have these other wonderful processes in our cells. We are constantly making DNA damage. Just the act of eating and metabolizing food, you're actually making, free radicals, which are attacking your DNA. And we have these wonderful DNA repair systems that go in and just clean it all up, and the cells divide, and we're rather a miracle that we're here and there are not giant tumors as it is. But cancer cells,
That's
it's true. It's
like
true. It's true.
It's a miracle that we are ourselves and not just tumors walking around
I'm
in
telling you,
civilization.
tumors with eyes. So
That's a sci-fi story.
Yeah,
right
yeah.
there.
Yeah.
There's a
I just
movie.
scared myself. So you have these cancer. So you have cells. These they become cancer cells. They're started by DNA damage, okay, or a mutation. I mean, that's the heart of what cancer is: a change to your genome, change to your DNA. But what happens with cancer cells is they go on to make DNA. Their DNA damage to themselves. They continue. It's called constitutive replication stress. They are continually damaging themselves. And you think about that, you go, why would a cell continue to make damage? It doesn't make sense. It's like, why are you continually mutating your own genome? But that is the way I look at it, and others, is actually it's almost an evolutionary mechanism for them. Like I said, every day we're making 8 cancer cells. We have this incredible immune system that's constantly surveilling and taking them out. So for a cancer cell to survive, it needs to constantly change itself so that it can avoid the surveillance system.
It sounds eerily like a virus, the way that you explain it.
It's diabolical. Mm-hmm.
Yeah. And, it's interesting that you mentioned the viruses because, there is been thinking for a long time, that ways to even treat some forms or cancer could we use things that, we use to target viruses? Could we use them for cancer? So, it's a scary thing. I don't want to scare your audience, but
you already have.
Yes.
So good things. So practice good health. Things that
Now I can't get walking tumors with eyes out of my head.
Yeah.
It's because of that. So what is this treatment that has 1996 in the title? What is this?
Okay, so it starts a long time ago. I never planned on being a cancer researcher. Well, I was going to be a space scientist, but I fell in love with the molecule of DNA. So my very early work had to do with, if you look inside the human cell, there's a nucleus, right? And inside the human, I always call the nucleus like the house of DNA. Okay, so in the house of DNA, the human cell harbors 3 feet of DNA inside the nucleus of every cell.
If you uncoiled it,
uncoiled it all out and stretched it out linear. 3 feet of DNA is shoved into something we can't even see. All right.
Wow.
And
if you took all the DNA of every cell and tied it end to end, that the person will die.
Well, probably, but also if you took all the DNA out of one human and stretched it out into space, it goes beyond the sun.
Wow.
Okay.
Just from one human? Wow.
Yeah, that's how much genetic information we harbor.
Yes,
that's how much genetic information we harbor. We are amazing machines.
And the person dies in that case too.
Yes.
Well, yeah, especially if you get close to the sun. So when every day, so our gut, we're like a tube within a tube. So your gut turns over like every 2 to 3 days, so there's a lot of cell division that goes on in your gut. And every time your gut cells have, or any cell in the human body has to divide, what you do is the mother cell has to make a whole new complement. So that's another 3 feet of DNA stuffed inside of one nucleus. And then those 2 cells in the DNA are divided out. So I got really interested. How does a human cell replicate its DNA in such a confined space and inside of like 8 hours? It makes that. There isn't a human machine that we have invented that can actually do anything near this with such incredible fidelity. So I got very interested. And so I got involved in studying DNA replication complexes. And then, as an independent investigator, I started reading about cancer. And cancer, is a disease of DNA damage. That's really what cancer is.
The crime scene of replication.
Yeah. And here, like Agatha Christie, here she goes. So I go and I said, I'm like the mother of replication complexes. I literally can isolate from a human cell a replication complex, put it into a test tube, offer it DNA, and it would make DNA just like, inside the cell. So I said, gee, I wonder if this complex is different in cancer cells versus normal cells. And I won't go into the gory details, but the bottom line was, yes, it was different in cancer cells. Cancer cells corrupt the DNA replication apparatus so that it allows a sprinkling of DNA damage every time it makes it. So actually, you can almost think of the daughter cells of a mother cancer cells are different from its own mother. That's how it changes. So I found that, and then we started looking, since I knew a lot of the proteins that were inside of this replication machine, I started looking through who was different. And we found one protein, which I didn't think would it be the protein. I thought it was going to be one of the cool DNA polymerases, but it wasn't. It was a protein called proliferating cell nuclear antigen, or PCNA. Now, way back when we first found this altered form of PCNA, people would never have looked at it. They always think it was like this. So it's called a sliding clamp protein. And I liken it, okay, like if you think of DNA as like a shower curtain rod, PCNA is kind of like your shower curtain ring. So PCNA is a sliding clamp protein and it circles DNA. And what it does, it tethers 3 other molecules that have to work at DNA and allows them to process and do whatever it is that they have to do. Now, the cool thing about PCNA, okay, interacts with at least 200 other proteins in the human cell. It has by protein-protein interactions. So we found that PCNA was different in cancer cells compared to normal cells, and that difference in PCNA correlated now with this funky replication act, right? So I got thinking, I said, suppose we technically we found a new molecular target, this PCNA, that's different in cancer cells. And it's not changed in the genome. It's not changed because of RNA. If I was to develop a drug to that PCNA, to the form that's only in the cancer cell and not in the normal cell, several things come from this. One, I would target and knock out only the cancer cell, because that drug would only be effective inside the cancer cell to kill the cancer cell. But it would also be super effective because it's not just attacking one protein, it's taking out an entire network of 200 protein functions inside of the cancer cell while leaving that same network in place in a normal cell. That is the heart of what AOH 1996 is. It is a molecule.
So this was a race to find something different about the cancer cell.
Yeah.
That had eluded people.
It totally is. It has so many novel features to it. I'll be very honest. When we first found it, everybody wonders, how come it takes so long to do, cancer research? Why can't they do these things fast? Well, we had this was found.
Is that what we sound like to you? Is that what
that's right. I do a lot of flying. I'm on a lot of airplanes, and I'll sit next to people on airplanes. This has to happen to you too, but I'll sit on airplanes and I'll tell people when hey, I'm a cancer researcher. I get a couple of different things. One is, they already have the cure for cancer. They're just holding it back.
Oh God!
Oh, really?
Gotta love those people.
That's what I get.
Yeah.
And then the other one
they
is
make so much money off of treating cancer. They can't cure it.
Mm-hmm.
And I'm just like,
and then
can
the
you
other
imagine
one
how much money they would make off of a cure?
That's what I always say. I said, and
what
then
are you
the other
kidding
one
me?
I always get. So then the other thing I get is, why does it take so long? Because, finding a target, moving it forward, and this target was so different. I actually went to a very large pharma company way back when. So this is when I first found it. And I said, hey, I found this great molecular target. Can you help me make a drug to it? And they said it was undruggable. That there was no way.
Why was PCNA undruggable then? What was it about that particular protein that made it?
It's changing. There's dogma. Okay, there's some dogma in the field, and dogma was you only make a drug against an enzyme.
Got you.
And so it was quite crushing to me when I went to this very large pharma company and I danced for them. I talked about replication complex. I was dancing for them and saying, this is a great target. And they very kind, they were listening to me and they said, undruggable. You'll never be able to make a drug to this. It's involved in protein-protein interactions. It's in a disordered protein region. It's impossible. And I just, when I left that place, I said, oh my God, how could I have been so, but by the time I made the parking lot of that place, I was like, I'll be damned. I'm going to try to figure this out. And with great fortune.
Wait, don't tell me you found a solution just to spite somebody.
No, actually I did it.
Whatever the motivation is, I guess.
No, I made a promise to a family that I was going to go and try to do something.
Okay.
About cancer.
Oh, wow.
Yeah.
So there's an underlying heart issue here. Okay.
I got to tell you,
there's a noble cause.
There is a very noble cause.
Yes. Spite sells better though.
Well, no, because, I guess spite would, but that's,
Let me just tell you something. When we make the movie, when we make the Linda Malkus movie about, the treatment and the cure of these certain types of cancers, the spite angle is what we're going to go with. Like the family will be the motivation, but the
spite is great fuel.
Yeah.
But it won't hold you for long term.
That's a very good point.
Agreed.
That really is a really good point. You
can only go so far because you just run out of fuel.
Yeah, that's a good point.
But when it's a heart issue and it's a promise, that's something else.
I'm going to dub you the queen of different thinking, just for the moment. Was there other different thinking that had to follow your initial thought process that obviously was different to everyone else's, that led you to AOH 1996 and its efficacy?
So you think about how this drug is working. It is very different. Okay, it wasn't an enzyme targeting an enzyme. I speak a lot in analogy. One of the ways that you shut down most of the air traffic in the United States is you send a snowstorm into O'Hare and you shut down all those routes. Okay, so PCNA is a terminal. Okay, it's
fantastic.
a hub. And you're shutting down 200 flights out. So literally what I'm trying to do is build a snowstorm to take out a central hub.
That's going back to this sliding clamp that you talk about, these proteins all being connected. And so what you're doing is you're coming in and you're saying, I'm not going to treat this. What I'm going to do is shut down the system inside of the system.
Shut down the whole network.
Right.
Shut down the whole thing. So
That's
that
amazing.
was really different. As luck would have it, this place called City of Hope called me out of the blue and asked me if I would be an external advisor for them to come in and review their research program. And so when I went there, I was blown away because they had put together this incredible apparatus, which I hadn't seen inside of an academic institution before, where they had put together all the people, the resources, and the facilities for actually taking an idea off a lab bench and moving it to the clinic. And I was like, this is where I got to go. So I moved to City of Hope, and they're wonderful. I've got with all these great minds, right? But I still had to do a lot of molecular biology, even to get them to be able to work on what I needed to do. And what I had to do was figure out where on the pCNA molecule was the business part for the cancer. And so what I did was I got the pCNA gene out, and we made mutations through pCNA. And we made antibodies and all kinds of things. And we were actually able to define a small domain of about 10 amino acids, which was the difference between cancer and normal. Once I had that address on the protein, so, every protein is so beautiful. Each one has its own crystal structure. If you look at the crystal structures, they're like their own. Every protein's like its own fingerprint. So I found on this big protein this little bitty address. But that address formed a pocket inside of the molecule. And once I had that pocket, that's when I could start screening for molecules. And we screened through 6.5 million molecules that would sit.
And these are humans, or is it some form of AI doing this?
It's a form of AI. So you use these gigantic. So this is so cool. I mean, this is called virtual screening. So they have, these fantastic computers, with, these databases of molecules and they're like from everything from trees and mushrooms and, from everything, any kind of structure so the 6.5 million molecules. And you take your protein, that 3D form of your protein, and I got that little packet sitting inside that protein. And you take that structure in that little pocket and you stick it in the computer, and the computer goes 6.5 million times this way.
Right, to see what puzzles
looking for
together.
those molecules. Right.
Right.
And it came up with 53. 53 out of 6.5 million. And we took them home and we tested 53 compounds on normal versus cancer cells. And of the 53 compounds, we found 5 that killed the cancer cells and left the normal cells alone.
Wow.
And it was like, oh my God, but that doesn't mean anything. It's on a lab bench.
And the work has been duplicated?
Yeah. So then it becomes this incredible process of, having that in what they call it a hit. So of those 5 molecules, we picked one. Mm-hmm. Very unique structure. Nothing looked like it chemically. And we moved it slowly forward through the process. So, and it became AOH 1996. It's in clinical trial now. It's in a phase 1 trial.
It's phase 1 with humans? So what phase is with other animals?
Okay, so
is that one of the phases?
Yeah, so the workup to get to the FDA, you have to do testing in animals. We did it in mice and dogs. And the beautiful part of it, of all that testing was, it did not show toxicity. We never found the maximum tolerated dose. The animals are very happy on it. I mean, they show they eat, they show no neurological problems. And in tumor models, animal tumor models, we show that we could inhibit tumor growth. And with all that data, you go to the FDA And then they granted permission now for the phase 1 trial. So we have patients that have been enrolled in the phase 1 trial. And the phase 1 trial, so there's 3 levels of trialing to move something to that, it can be used in the clinic. Phase 1 is a toxicity trial. What can we find the maximum tolerated dose in humans? And I have a strong suspicion we won't. And then you go on to now efficacy trials. Those are called phase 2 trials, where, you're testing, do you see any effect on a person with tumor? And then phase 3 are these large trials, over different populations.
You describe cancer as a molecular signature disease. I can say that, but I'm not quite sure I'm anywhere near qualified to explain what that means. So would you, in terms that I might understand, what that actually means? Because you don't see it as singular. You see it as multiple diseases, don't you?
Yeah. So when I was learning, I was training, cancer was really thought as like one thing. You had breast cancer, you had lung cancer, you had prostate cancer, you had whatever it was one type, right? And I used to work with a wonderful breast cancer oncologist out in Indiana, and he said it would drive him crazy. He said, Linda, I'd have 2 women who come in with breast cancer in my practice, and everything about them is the same. They grew up in the same street. They have, they have the same number of children. Everything I could measure about them was the same. He said, I would put them on protocol and one would respond beautifully and one would die. And there was no way to tell the difference. That was our thinking for so long, that, cancer was one thing. That has totally been radically changed now. Because cancer is probably as individual as your fingerprint.
Well,
cancer as it affects the individual.
Yeah.
Yes. So you think about your tumor now. Your tumor has its molecular signature. The thing there's a lot of unique features. That's why, this molecular signature part of cancer is such a huge breakthrough. Where they call it precision medicine now, right? Or moving towards precision medicine.
Is that the same thing as designer medicine?
You're getting there. Seriously, you're getting there. Okay. So if you if you can think the other thing that we had very myopic vision was that tumor was all by itself, but you also have to recognize that the tumor is sitting inside of a host. So there's the environment around a tumor is going to influence cancer activity just as much as the tumor itself. So
if I'm not serving dinner at home, I don't like being called a host. There's something about that.
I'm cool with it as long as there's not a parasite involved. I'm all right with it.
Well,
that's what says my whole point.
I'll tell you, cancer is a parasite. It just hasn't figured out how not to kill the host. It is a parasite. Right. I mean, cancer is a parasite. So now a person comes in to clinic, you have their genome read, and you can actually figure out, we're moving to this. We already do it in some cancers. But you look at their molecular signature and you're starting to say, oh, well, this drug works better in this place. And, and even if even if the drug was found in lung cancer, but a woman could come into the clinic with breast cancer with the molecular signature of the tumor that would really work well with a lung drug. I mean, it's really amazing. We're really in a very, very different kind of time and a revolution in time in thinking.
Wait, so what is the evidence that one kind of cancer migrated from one organ to another?
Okay, though that's
because many women with breast cancer die of brain cancer.
No, I don't want you to get confused. I don't want you to get confused.
Yeah, I don't want to. Yeah, so
so there's actually
me, please.
2 things going on. One is metastasis. Where like a woman has a breast cancer, and they will likely metastasize to bone or brain. I mean, it's kind of like it has a homing device. It will go there. It likes that environment, you know. The other thing but I want to stress is the molecular signature is not about metastasis. Sometimes the things that are helpful to a tumor to grow, whether it's breast or lung, are the switching on or off of particular genes. That is a molecular signature that could help us potentially either use current therapies or make new therapies for. That's a base molecular signature. Metastasis is a whole nother animal.
So you said that we produce 8 cancer cells per day. How does this treatment differ in our body's eradication of those 8 cells? And why don't we just try to replicate what the body, so you have this antigen, is our body making an antibody that actually just kills these 8 cells? Exactly how is the body killing the 8 cells? And why aren't we trying to replicate that?
So it's good that you bring these things up. So that, one of the big arms or areas of research that is going on is immunotherapy, right? It's like harnessing the power of the immune system. And so you have, they call them CAR T cell therapy. There are immune checkpoint therapies. Huge. This is an amazing question. Obviously, in a fully functional person, our immune system is keeping things they're keeping cancer in balance. You're in check. They're keeping it in check. Whatever reason, we become out of balance, or you're exposed to some environmental cause, body doesn't maintain that balance anymore. So there are wonderful arms of research. Some it's going on at City of Hope, very, very exciting, where they are exploiting now or trying to understand how to better harness the immune system. But the thing is, but I have to go back. Cancer constantly is figuring its way around things that we throw at it. Way back when I was training, everybody said, we're going to find the cancer gene. It turns out there's lots of cancer genes. I do not believe we will ever have a single therapy. What we will have is, and I believe AOH 1996 is going to serve as one of the agents in an arsenal. We already have an arsenal. But the object is, with using precision medicine, that we are able to turn cancer from a critical disease into now a managed disease. And we're moving towards that. I actually have a friend who had breast cancer and she never went into remission. She lived for 12 years with cancer.
Oh, that's kind of like prostate cancer. Most men die with prostate cancer because it's such a slow growing cancer that sometimes it's like, well, we keep an eye on it. There's no need to do anything invasive because you'll be dead before it kills you.
Yeah, but it's a very painful cancer for men. It really is.
I did not know that.
I know, actually, in some, if it progresses for them, yeah.
May I ask you, AOH 1996 is administered as a pill.
Yes, twice a day.
Why a pill?
So why a pill? I wanted to make it easier on the patient, as opposed to them having to be hooked up to infusion, but also based on the chemistry of the drug, it has a half-life of about 5 hours. And so in order to keep the drug present all the time, it needs to be administered twice a day. So it didn't, patient isn't going to come in and be hooked up to an infusion, all the time. So it's a continuous, the patient comes in, they are, our phase 1 patients come in, they are, checked for, certain how they're doing and everything. And then they're given their pills and they go home and they take it. And so they take it twice a day.
So Linda, I heard you use the term half-life. Is that in the way we would use that term in physics? Where after a certain amount of time, there's half of the thing that matters that's still active
yes,
going on?
Absolutely. Absolutely. So the body, the drug is metabolized, eventually.
Metabolized. That's what eats it up.
Yeah. So it has a half-life metabolism. Yeah.
Oh, so cool. After 5 hours, there's half of the drug, and after another 5 hours, half of the half. That was
right.
Half of the half, and so then you got to pick it back up with another dose.
Right.
So I get it. Okay.
Yeah, that's like like anybody taking antibiotics. Some people have to take it 3 times a day or twice a day. It has to do with maintaining a drug.
I know. I understand it precisely with that terminology, but I've never seen the term half-life on a bottle of drugs.
They should put it on there. And you know what?
It's behind the label.
Yeah, they should put it on there because it's so important. Like when you said antibiotics, a lot of people screw up their antibiotics because they're not taking them when they're supposed to take them, or they don't finish them. And it's so important that you do that because of that reason. So maybe they
half-life, they might make it a little more urgent.
It might make it more urgent if you said.
Actually, that's actually for any drug, if they say, take it every 8 hours, it all has to do with the drug half-life.
Right.
Yeah.
That's a good thing to know.
I will henceforth think of it in those terms.
Yeah.
Yes.
Yeah. Because that's
the half-life of my asprin, right?
Yeah. So
I'll tell you the half-life of aspirin, children.
All right. You said AOH 1996 would most likely be most effective as a combination therapy. Is that going to be beneficial for cancer resistance as opposed to like a single pathway therapy?
It's actually a wonderful question, Gary. Thank you. So one of the problems with cancer, it's a pain in the butt. Remember, it's this evolutionary thing going on with cancer. So a woman has ovarian cancer or a person has lung cancer, and they are treated with usually with a platinum compound right off. And
what's a platinum compound?
So they're chemotherapeutics that attack attacks DNA. So but it's also very toxic because it can't tell the difference between a normal and malignant cell. So it's targeting proliferating cells, which are cancer cells, but you also have a lot of proliferating cells
that are healthy.
And that's why so many chemotherapeutics are horrible, because they're targeting proliferating cells and they can't differentiate it between normal and malignant.
So, for example, as we came to understand it, your hair grows faster than most other things in your body. So that would be a byproduct of the targeting of proliferating cells. Is that correct?
Yeah. So your eyebrows, your toenails come off.
Right.
These are horrible. These side effects are horrible. You lose, you lose your eyelashes, your tongue, your gut. Remember I told you your gut is turning over 2-3 days rapidly. That's why so many chemotherapeutics really have such bad GI effects. But going back to Gary's question about combination therapies and resistance, well, one with AOH 1996, if it holds up for being very non-toxic and effective for treating cancer, of course, you can now, what you do is and not just AOH 1996, this happens all the time. The thinking now is it makes Big Pharma unhappy because they always want one big drug, that's going to treat everybody. But now that the one big drug, or they call it monotherapy, we're moving away from monotherapy and more going towards what they call cocktails, is that you will put together a variety of drugs, like treating testis cancer.
Chuck knows a lot about cocktails. Chuck knows.
I knew that gag was coming. That was,
Yes. Yeah.
So my joke is that AOH 1996 will be the olive in everyone's cocktail.
Ooh.
So like that.
Look at that.
Yeah. So,
Ooh.
so two things with AOH 1996. Great hope down the line if it proves to maintain its non-toxicity. I hope that we've already done studies in animals to show that it complements a variety of currently used drugs. And in the presence of our drug, we can actually lower the amount of some of these very toxic drugs very significantly. Right. So the animals can have, they can still show very effective growth inhibition of the tumor, but they're not sick. But your thing about resistance, this has come up a lot for me for this drug, for AOH 1996. My lab has worked really hard at trying to make resistant cancer cells. Cancer cells love to do this. Yeah. I mean, like I was talking about the patient, the lung cancer, ovarian cancer patient, they respond beautifully, but in a year or two, their cancer comes back.
Right.
And they're resistant now to like cisplatin or carboplatin. AOH 1996, we can't make a resistant cell so far. And I'm thinking, why? If I, like a lot of the therapies that are made against kinases, single enzymes, remember they do one function, and what the cancer cell can do, because it's such a little, it goes, so you're treating, like with a kinase inhibitor, cancer cells will now change the enzyme that used to target, okay, that drug would target. So now it's resistant to the drug. Right. And cancer figures a lot of different ways to become resistant to drugs.
It's just amazing.
Cancer is like amazing.
It's unbelievable. Is there such a thing as cell intelligence? I'm trying to figure out, because as I hear you talk about this, and I'm thinking about viruses and these cells that tend to adapt and change and reconfigure. It's like, what is going on that this can happen? Is that just part of our evolutionary process? What is going on?
It wants to survive.
I'll take a stab at that.
Go ahead.
There's billions of them.
Yes, exactly. Billions and billions.
Yes.
So most will die because they can't adapt to the thing. The few that do, bada bing.
There you go. That makes perfect sense. Look at that.
Bada bing.
So Linda, I just spoke up out of turn.
No, you did great. No, you did great.
There you go. You did good.
So Chuck, when it's a game of numbers, there's always somebody who's going to slip through the gate.
Yep. Look at that.
Yeah.
And remember, and it's constantly changing its genome. It's like locks, it's changing the locks.
Right.
So with resistance now, what I'm thinking with our drug, it's not a single enzyme. It's a hub. You'd have to change all those gates.
Right.
All those proteins coming in and going out. So I have this, I have to write a paper on it. I'm going to, for the first time ever, and I probably shouldn't do, but I have the hubba hubba hypothesis for treating cancer.
Love it.
Hubba hubba. So by attacking a hub like PCNA, because it controls, all this network, if we could identify other networks like PCNA and start targeting hubba hubba,
right,
you really would be shutting down cancer cells. Of course, you have to find them very cancer specific, but as opposed to the very long time strategy of just targeting a single enzyme, as opposed to start targeting a single star, you do a whole galaxy, You target galaxies, hubba hubba.
So Linda, take us out here. In 5 years, 10 years, what does the world look like?
Things have changed so much in the cancer therapy field just in 10 years. From my training in the last millennium, okay, last century, where we thought, we're
Yes.
going to find one cancer gene, one drug's going to do it all. We were so naive to now the basic understanding that everyone's tumor is different. But now with using molecular signatures, we're getting every tumor's address. We're figuring out where they live. Okay. Not just locally. But
I know where
figuring
you
out
live.
they
There you go.
I know where you live, cancer. I know where you live. Yeah.
That's exactly what we're being able to do.
Chuck is getting Philadelphia on you right
Oh,
there.
Yeah.
Come see.
Backwoods, Phil.
Well, you don't have to come see me. I'll come see you.
Exactly.
Okay.
Exactly. But the thing is with figuring out the underlying molecular signature of each person's tumors, their personalized signature of that tumor, and now coupling it with this molecular signature, you respond to these subset of therapies. So when a lady comes in with breast cancer, you can say, Mrs. Doe, you have breast cancer 6A. And we know that 6A responds to this cohort of drugs. And we'll effectively treat her.
Wow.
And she may be cured. And if she comes out of remission, we check that signature again. And we say, wow, we use this cohort of drugs. So I see great things.
You're going from carpet bombing to precision targeting.
Yeah.
It's amazing.
Drone strikes, baby. Drone strikes.
Drone strikes.
It's like walking, Chuck. It's like walking into a store, buying a suit off the peg, or going to Savile Row, where the best tailors in the world are, and getting a bespoke,
exactly,
bespoke just for you.
There you go. That's fantastic.
Bespoke drugs. All right, Linda. You said you're from Queens, New York. Is that you're in LA now?
Jackson Heights, Flushing. Yes, yes.
Cancer never stood a chance. She's from Queens, New York.
What high school did you go to?
So high school, I went to St. Agnes in College Point.
St. Agnes, okay.
Yes. And then school, I'm a graduate of City University of New York, Queens College.
Wow.
CUNY. All right. Well, Linda, thank you for being on the show. Oh, my gosh.
Thank you.
We like intermittent beacons of hope, which you have offered us all as we proceed here. And, this special edition, StarTalk, is all about many things, but the human condition especially. And you're at the center of that for so many people out there. So thanks for sharing your expertise and keep at it. Stop talking to us. Get back to the lab.
Absolutely. They're in there. Okay. They're in there working. Trust me.
All right. Gary, always good to have you, Gary.
Pleasure. So glad we had a chance to tell this story.
Yes. All right, Chuck. Good
Always
to have you there.
Pleasure.
Neil deGrasse Tyson for another edition of StarTalk Special Edition. As always, as Linda taught us once again, keep looking up.